So, should I start or?
So now we can start.
Um, Good afternoon, everyone. So, this is my second lecture. The first lecture already I gave 1 day back. Uh, so, this is, I think, the last lecture of this series. Okay. So, the first lecture on 24th, I explained what is actually the nanomaterials or nanoscience, nanotechnology, and what are the special properties of the material uh, that I have discussed in detail. And last slide of the last lecture, I told like this lecture I will give mostly on like by using those properties, how we can actually synthesize the nanomaterials and what are the controlling factors of synthesizing this material. And once we synthesize, how actually we can apply it for different applications. So, this lecture mainly I will explain like what are the fast and slow kinetics by which we can synthesize large or small nanoparticles, and that actually ultimately give us like the asymmetric and symmetric materials, and that also generates the defective and non-defective materials, and why we want to generate the defective and non-defective materials, that I will explain in details. So, so like once I start the lecture with fast or slow kinetic, so then this is one of the report in 2019, very recent report, like the chemical reaction, how fast actually we can think it can happen. So it has been found that the abstraction of hydrogen or adsorption of hydrogen onto the graphene surface, which actually occurs is a lightning fast, or which is about like 10 to the power minus 14 second, which is about like 10 femtosecond. So this is one of the fastest reaction we could now still we can record. So the graphene, as I explained in my last lecture, so there are a series of in 1990, the series of carbon nanomaterials came into the market, and those are like carbon nanotube, single wall, multi wall carbon nano. Similarly, in 2000, uh, around 2004, I think, yes, 2004. So that was Professor Game and Novoslov. So both the Russians. So they made actually the graphene, first report of graphene. So the graphene, which is actually a zero band gap material, there is no gap between the valence and conductors. But those things, the application we don't find much. But once it absorbs the hydrogen, actually this gives a huge application in semiconductor or insulator industry. So this is just, you can note down that this is one of the fastest reaction in the history we could record. Similarly, like in the natural phenomena, like if you look towards the high energy physics or cosmology, so you will see like there are several phenomena which are actually very fast. Like at the if you look at the beginning of the universe, which starts with the Planck epoch or the era, which is about like 10 to the minus 43 seconds, and then grand unification epoch, which is 10 to the minus 36, and the inflation epoch, which is the like extremely rapid expansion of the universe took place in 10 to the minus 32 seconds. And then gradually, like when we look at the nucleosynthesis, which is familiarly known as the Big Bang, so which is about like 10 to 1000 second time scale. So where actually the material starts actually forming, which are like very simple materials, atoms or a clusters of atoms like hydrogen, helium 4, and then deuterium, helium-3 or lithium-7. So initially those materials started synthesizing. So that's from there actually the chemistry appears. Not only that, actually in the femtosecond time scale also, experimentalists have actually already found from the femtosecond time resolved X-ray scattering method, like how the gold atoms come close to each other and make a bond. And very easily from this data you can find the bond length as well as their conformation, how the gold atoms actually coming close to each other to make a cluster. As you can see in the 5 picosecond, so the things are like they are arranged. Okay. So and even in 200 femtoseconds, the three gold atoms comes close to each other. Okay. And in 10 nanoseconds, they make the clusters. Okay. So these are the very fast kinetics or very fast dynamics of like how we can observe them. So this how fast or slow of the reaction, does it depends on the reducing environment? Yes, the answer is yes. Like if we consider a very simple reduction, like gold 3 to gold 0, how actually it depends on the condition or the environment. Okay. So like this is one of the example, like when we synthesize gold nanoparticles, then how actually different nanoparticles synthesize in different time scale. Like if we think about a slow process, like just think about the flowering. Okay, so from the bud, how actually it blooms. So it goes through several stages. So this is a very slow process. Similarly, nanomaterials also like starts from the seed. How if you look at the step by step from left to right, then how actually it takes time actually to grow and finally overbloom. Okay, so this is a very slow process. Like this total process, it takes about like 3 to 4 hours. And each step, if you record actually, how actually they structurally they evolve like like one from one structure, it does the transition to the another structure. So that's actually defines the how slow is the reaction process. So this is very easily we can explain like a baby, how from a gamete actually it finally forms to a baby. So it took about like 38 months, okay, 38 weeks. So that's the way the baby actually formed. So you see that as the process you intentionally you make it slow, so then you can see a baby comes out with such a nice structure. It has hands, legs, nose, eyes, teeth, everything. So anyway, the same way, if you actually also controls a reaction or if you control the kinetics of the nanoparticle synthesis very slowly, then actually each facet, how nicely they will build, and then finally you will get a highly structured nanomaterial. But on the other way, like if the reactions occurs in very fast process, so then the system doesn't get enough time to organize the atoms in a particular direction. So then finally we'll end up with a spherical particle. And that's the way that if you look at the universe, so they actually this Big Bang happens so fast. So then all the planets, everything, so they are kind of like a spherical structure. But in nanomaterials, we can see that those materials which are synthesized by very fast kinetics, most of them are spherical. But on the other way, those actually grown by very slow process, most of them are anisotropic. So anything, if we want actually to grow as an anisotropic or a structured material, then we have to slow down the process so that a particular facet actually nicely extends and gives a desired result. Okay. So this is very simply we can understand. Like it's nothing like very tough to understand. It's like you just think about like the dissociation of water. So water, how it dissociate? It will dissociate either to H plus and OH minus. So at 25 degrees centigrade, the equilibrium constant Kw, which is 10 to the minus 14. Now think about we are trying actually to synthesize some nanoparticle of gold. So generally we take the precursor as gold chloride or auric chloride, which is HAUCl. So this is a salt. So as soon as it goes into the water, it dissociates into H plus and AuCl4 minus. Now you think about that, this is a salt. So in the solution, it will automatically dissociate into H plus and AuCl4 minus. So the system has enough hydrogen plus. Okay. So since the system has enough hydrogen plus, so it doesn't need any more hydrogen plus comes from the water. So the water equilibrium will move towards left. So that means water will remain as water molecule. So this is simply the in chemistry call it the last Sapelius principle. Okay. If the conditions is favoring a product, so then the equilibrium will move towards the opposite direction. So H2O will remain as H2O only, and HAuCl4 remain as H plus and AuCl4 minus. So now suppose we want to reduce this gold. Here gold is at plus 3 state. Okay. The gold we want to reduce it by trisodium citrate, which is a reducing agent. So trisodium citrate, how it dissociates? It dissociates into 3 sodium plus and citrate 3 minus. This citrate will abstract hydrogen plus from the water. So the water hydrogen plus will be a deficient one. So the once it's abstract the H plus from the water molecule, so the equilibrium will move towards the right hand side. Okay, and then Ct3 minus becomes CtH2 minus. Then CtH2 minus again abstract another hydrogen plus and will move to CtH2 minus. So by that way, it will make the CtH3, which is citric acid. Okay. But every time when it abstracts one hydrogen plus, so that time actually the equilibrium of H2O move towards the right side. So that means the system also generating the OH minus. So those OH minus finally will reduce the gold 3 plus. Okay. So you see, so this doesn't happen in only one state, but rather it goes to a cumulative state. Okay, so that's why the reaction kinetics is very slow when we reduce it by trisodium citrate. But now think about when we use the reducing agent as sodium borohydride. So as soon as you give the sodium borohydride mixed with water, okay, so this is a very hygroscopic, and then immediately sodium borohydride will generate, each molecule of sodium borohydride will generate 4 nascent hydrogen and NaBO2. Okay. This 4 nascent hydrogen finally will make a 2 molecule of H2. So that's why, like, if you want to use this nascent hydrogen as reducing agent, you need to slow down this reaction kinetics by dissolving the sodium borohydride in ice cold water. Okay, and since this is a single state, it generates the hydrogen plus hydrogen, nascent hydrogen. So this nascent hydrogen itself, which has only one electron, so that immediately acts as a reducing agent. You see, you don't have to go this hydrogen to generate a step-by-step method. So this will act as a very fast reducing agent. Okay, and the kinetics will be very fast. So that's why anything we are using any reaction by using sodium borohydride as the reducing agent, the reaction kinetics is very fast. And if we use trisodium citrate or equivalent reducing agent, the reaction kinetics will be very slow. So in the case of sodium borohydride, most of the time the experience is we generate actually the spherical particle because the reaction kinetics is very fast. On the other hand, the trisodium citrate, ascorbic acid, oxalic acid, all weak reducing agents, the reaction kinetics is very slow and we generate the anisotropic materials. Okay. So now you'll see, like, most of the times when you are using a harsh conditions like high temperature, if something you want to reduce it by boiling, okay, or high pressure, okay, strong irradiation, large fields, field can be electrical, magnetic, or photonic, whatever, or strong reducing agent. and low viscous. So strong reducing agent, as I told, the sodium borohydride, lithium aluminum hydride, all or the nascent hydrogen. Those are the strong reducing agent. Or even low viscosity. Low viscosity means the ions or the reducing agents all are very mobile. So they can come close to each other very fast. Okay. So all those things actually favors a fast kinetics. So this fast kinetics will give you the spherical particle. Now the fast kinetic system actually, as I told, like that doesn't get enough time for systematic crystallization. So if the system doesn't get systematic crystallization, so all the ions they will come close to, or the atoms they will come close to each other, and then finally it will make a spherical particle. So as you can see, like this scheme, so you can see like how actually when we make different particles, okay. So either they will be spherical. If you see the spherical, then the properties in all three directions, like X, Y, and Z, so they are same because they are spherically symmetric. We call these type of particles as isotropic. And the other particle which has a directional property, as you can see, like A2, the length it has, it's not a spherical, it's kind of like an oval. So the properties in X and Y is different from the properties in the Z direction. So that's why these properties called as the anisotropic part. And also you can see like in the B plot that when we consider different shapes, so there are 5 platonic solids. The solids are like, so all of them actually evolved from the sphere. So those are tetrahedron, cubic, octahedron, icosahedron, and dodecahedron. So you see, like the per sphere, it has the lowest surface to volume ratio, whereas the tetrahedron has the highest surface to volume ratio. So that means tetrahedron has the maximum exposed surface area. And as the surface area exposed more per volume, the reactivity is also the maximum. Those things I will come later. So now, since I told like this lecture, mainly I will focus on the generation or the synthesis of different type of nanomaterials. So, as explained in the previous lecture also, there are two methods. One is the top-down approach, where the physicists generally take this approach from the bulk material. We can grind them, or by adopting different physical methods, finally we can make the nanoscale material. But for the chemists, generally we use the precursor as a metal precursor. Like for gold, we use HuCl4. For silver nanoparticle, generally we use silver nitrate. For copper, we use copper sulfate, copper chloride, and then we generally mix with a reducing. So that could be a strong reducing agent or a weak reducing agent. And also we use like a surfactant, okay, which will stabilize the nanoparticle. This surfactant, it could be trisodium citrate, it could be SDS, okay, it could be polyvinyl pyrrolidone, it could be cetyl trimethyl ammonium bromide, cetyl trimethyl ammonium chloride, all sort of ligands are available in chemistry. So by using this method, like a metal precursor, a reducing agent, and a stabilizing agent, we can actually adopt different synthetic protocols. Depending on what structure actually you want, you can actually get the desired. Okay. And there are, as I mentioned in my previous lecture also, so there are two types of synthesis. One is a single step synthesis, where everything you mix together and then they make an nanoparticle, or there could be a step by step synthesis. So where you can make the seed, you can grow the seed to a bigger particle, you can use that bigger particle as again seed to form the final desired particle. Okay. So these are some of the chemical roots of nanomaterials. What are these roots? The, as mentioned, like the first one is single step synthesis. So single step synthesis, what we do? So we use the metal precursor, we use the surfactant, and then different condition to reduce it. Okay, it could be a reducing agent, it could be thermal energy, it could be photothermal energy, or it could be a radiation, whatever. So all by adopting all these conditions, we mix all these chemicals together in a single step, we can synthesize a nanometer. So as you can see, all these nanomaterials, initially we used to think that by one step method, we can only synthesize the spherical particle. But now actually we found that not only the spherical particle, but also other shape particle also, like flower shape or rod shape particle. So in a single step synthesis, we can generate. Now there are multi-step synthesis. Multi-step synthesis means like first we generate the seed, and that seed we use for making the bigger particle with variable shape. So it's commonly known as the seeding method. Okay. So in these seeding methods, like this is one of the synthetic method where we make a seed, which is a negatively charged seed, and by using that seed and cetyl trimethyl ammonium bromide as the surfactant, thus simply by varying the concentration of the cetyl, we can actually make different shape of the particle. Now there are another method which is a kind of like a three-step synthesis. So those are nano templating. What is this? This is like first we make the seed. So then by using this seed, we can make a finite size nanoparticle. So these are like nano popcorns. So these popcorn shape nanoparticle, we can generate about like 50 nanometers. Okay. So now this 50 nanometer particle again we use as the seed to generate different shapes of particle. So this is a three-step templating, nano templating, or we can use a multi-step layering or assembly. So like instead of three steps, we can use several steps to use a material. So like here it's very simple, like the core is a gold, and then use this core gold as the seed, we can put a layer of silver. Okay, and then again use that as seed to make another layer of gold. Again you use this three layer as a seed to grow a fourth layer of the silver. So by that way you can make a multi-layer structure, or even you can actually use like a gold bar and then add a silver bar and then use a gold bar and silver and gold. So periodic way you can, or even in the three-dimensional you can actually arrange these materials to get an anisotropic manner. So the facility of this synthetic route of nanomaterial synthesis we generally adopt for large scale synthesis because it has few advantages. What are these advantages? So first of all, this is a method by which we can produce the materials in a large scale, like kgs, okay, tons, okay, metric tons of nanoparticle we can synthesize in the solution. Okay. So that's why it's the process of large scale production. And also like you can see like there are several conditions, like there are several physical conditions, like you can change their viscosity, you can change their temperature, you can change the different radiation, you can change the pressure. So by changing different physical parameters at the same time the chemical parameters, like you can change the ligand, okay, you can change the metal precursor, you can change their pH, okay, you can even change their composition. So by changing this physical and chemical condition, we can easily manipulate their structure as well as their composition. Okay. So the shape, size, composition, everything we can actually manipulate by changing this physical and chemical parameters. So like the availability of large number of control factors. Okay, that's fine. And then the time efficiency. So like for anything like top down myth. So these are not only very costly but also you need much longer time to generate a certain amount of material. But these are within few hours actually you can make large amounts. So this is also a time efficient. And also, as we know, like the hard chemicals are as not as that expensive. So we can actually use those things to generate materials by low cost. Okay, so those are all low cost materials. And also, like efficiently, we can make layers material. So as I explained in my previous slide, like we can make them layer by layer. Okay, so those have a very good applications in the modern generation capacitors, okay, batteries and other things. So for the energy sector, that has a huge application for the layered material. And also like atomic scale precision, like by simply varying the conditions, okay, factors, we can actually we can manipulate the atoms or molecule, how actually they will be decorated on the surface. So since all these all these factors are so easily we can control, that's why the synthetic route of nanomaterial synthesis or the chemical route of nanomaterial synthesis is so much accepted. Okay. So by using all those things, we can actually, as you can see, like we can make any sort of geometrical shape. So like that starts from a spherical particle, rod shape, to popcorn, prism, to wire shape, to flower shape, to needle shape. Okay. And also like something you can make a, like a prism or a thin plate where there is a each plate at the center of gravity there is a hole. Okay, so these are kind of like a beads. Even by using the a long chain ligands, we can attach one after another to the centers and make a small garland. Okay. Also, you can make like a cubes, okay, or bipyramids, okay, plates, all sort of structure actually you can make. And also in the literature, you will see there are all weird structures. Okay, you can make like nano carrots, okay, nano boots. Okay, I'm not going to describe all those things. So, like whatever the shape you can think now, actually people are trying actually to make those things. Why they are making? Because we know now like the properties of the material that heavily depends on the shape. So some shape for their specific shape they actually shows a very different property. So to in search of those properties, okay, people are making different structure now. Not only we can make, but also we can make a assembly. So like the rods, so geometrically we can assemble them so nicely in a dense way. Okay. So this is a, by a ligand method where a ligand in between two rods by they actually can be joined. Just think about a small chain thiol by dithiol. So the both sides the ligand has a two sulfur. Then each end of the nanoparticle, one sulfur and another end to the another nanorod, they will join together. Can make a 2D material. So there are materials we can make all in like the zero dimensional, one dimensional, two dimensional, and three dimensional. So one dimensional means it's a spherically symmetrical, or we can think about it isotropic. So that could be a single sphere, or it could be collections of sphere with the collection itself also a spherical structure. Then it's a zero dimensional. One dimensional, these are generally we define not by rod but rather by wires, where the diameter of the rod is very thin while the length is very big. Okay, so that's why the aspect ratio, which is length by the diameter, is very high. So those we call as the one dimensional nano. Then it comes like two dimensional, like we can make a plate, okay, we can make a sheet, okay, we can make a prism, okay, thin slices prism. So those things are the two dimensional. And then three dimensional where all the x, y, and z will be there. So these are like cubes, okay, or some other platonic solids, okay, we can make. not only this making of this individual, but also like the nano assembly, we can actually make them a superlative. Like the only thing is that you can make a lattice structure. The lattice is made by the atom. So here also, instead of the atoms, we are making a lattice by the nanoparticle. So think about then the nanoparticle has to be so much symmetric to each other so that they can actually make a nano lattice. And that infinite direction, if you think, then we can make a super lattice. Okay, so those also we can now effectively we can generate. So now to generate those things, okay, we can actually control the different factors, or we call them as the factors which controls their anisotropy. Okay. So what are those factors? As I told, like there are some physical factors and as well as there are some chemical factors. So those factors are like the pH, okay, or the head group, or the reducing agent, whether that's a very strong reducing agent or it's a weak reducing agent. Okay, whether the head group is a positively charged or negatively charged, or even like the facet energy. I'll come later, like how actually the facet energy is also controls the anisotropy of a nanometer. So let's one by one. So first I'll describe about the chemical parameters. The chemical parameters, out of several chemical parameters, the most the effective chemical parameters which controls the shape of an nanometer is the reducing. The reducing agent, as you know, like the reducing agent, either it could be weak reducing agent or strong reducing. The weak reducing agent and the strong reducing agent. So the strong reducing agent, what are those? Like sodium borohydride, lithium borohydride, lithium aluminum hydride, or sodium cyanoborohydride. These are very strong reducing agents. Means like as soon as you give or put it into the solution, it will immediately dissociate and generates the nascent hydrogen. So this nascent hydrogen acts as a reducing agent. So that's why the chemical kinetics is very fast. That's why we know that those things as the fast reducing agent or the strong reducing. But on the other hand, there are some which are weak reducing agent, as I explained for trisodium citrate. So here also, along with the trisodium citrate, there are like ascorbic acid, okay, or oxalic acid, formic acid, all actually they act as the weak reducing agent. So you clearly you see this left hand leftmost picture and the middle one, all those are actually formed by the strong reducing agent. You can see that these particles they look perfectly spherical. Not only that, even if you zoom it, go for the high resolution case, then also you can see that they are mostly spherical. Okay. But on the other hand, when we use the weak reducing agents like ascorbic acid or oxalic acid or formic acid, then you can see that they are no more actually spherical, but rather they are highly anisotropic. They give sharp tips, okay, sharp facets, okay, edges, so all sort of things. So they give. So those are we call as the anisotropic. Not only the reducing agent, but also the templating agent. Templating agent means like the here we call as the safe-directing ligands. Okay, safe-directing ligands also play a big role in forming a different shape of nanoparticle. So you see here I specifically gave 4 examples where all are ascorbic acid base reduction. So I'm keeping the reducing agent constant, which is ascorbic acid. Okay. Now by using different surfactants, like I use 3 specific surfactants. One is CTAB for the first, second one is also for the CTAB, third one for the trisodium citrate, and the fourth one for PVP. Okay, so out of these force, you see, when we use the CTAB, so sometimes it gives the popcorn shape, sometimes it gives the rod shape. But when you use the trisodium citrate, so they gives a sharp tipped nanoparticle. But if you think about the spherically, these are symmetric. Okay. But on the other hand, when we use PVP, polyvinyl pyrrolidine, at that time you see instead of sharp tips, it gives a plate structure. So that means it heavily depends on the ligand, okay, or the shape directing ligand. Okay. Not only that, it also depends on the head group. Head group of the surfactants means, so what are the surfactants we are using? Like we can use CTAB, cetyl trimethyl ammonium. We can use cetyl trimethyl ammonium chloride. We can use ethylene glycol. Okay. We can use SDS, sodium dodecyl sulfate. So then, depending on the head group, they forms different structure. So you see the top one, left one, top left, the structure looks like a flower, which actually we use the SDS as the surface. Similarly, the right hand side one, so they looks like a wires. Okay. Now, instead of nano rods, so they are nano wires. These are very long, it's like 50 micron. So those we can actually generate by ethylene glycol using as a surfactant. The bottom left one, we can use cetyl trimethyl ammonium chloride, where the rod size are very small. Okay, but instead of cetyl trimethyl ammonium chloride, if we use cetyl trimethyl ammonium bromide, then we can see that we can generate a nice rods with a much better high aspect ratio. Means the lengths are much bigger than their diameter. So you can see like depending on the head groups. So head group means for sodium dodecyl sulfate, but the head group is sulfonate, which is a negative charge. But for the CTAB and CTAT, cetyl trimethyl ammonium chloride, the ammonium chloride, which is also a positive one, and for CTAB, cetyl trimethyl ammonium bromide, so there also trimethyl ammonium group is positive charge. So depending on the head group, actually it forms different shape of the nanoparticle. How actually it occurs? So you see, like most of the time when we synthesize by suppose this, so this is a specific example of SDS, okay, sodium dodecyl sulfate as the sulfate. So sodium dodecyl sulfate, so it has a long chain and the sulfonate group SO3 negative, SO4 negative. The SO4 negative is negatively charged. So they will immediately, when it goes to the water, it makes a micelle. Okay, because we generally we use the concentration of SBS much higher than their CMC value. So the below where I wrote actually suppose this synthesis where we use SDS as 0.01 molar, but the CMC of SBS is 0.0082 molar. So that means we are using actually the concentration larger than their CMC. The CMC is the critical micellar concentration. So above the CMC value, so what they will do? So they will make a micelle. Now, since we are making it in the water solution, so the head group will be projected out into the outside or the towards the water solution, and the long chain will be directed to the core. Okay, so that's the way the micelle. Now, once we add gold is, so the head groups are all negatively charged. Okay, now the gold is positive. So gold will go where it will go? So gold will go and attach to this negatively charged here. Okay. But once we reduce it, the gold, all the gold will be instead of positively charged, so it will be neutral. So they will not actually find a very electrophilic attraction in the outside domain. And then they will finally move towards the center because that's the hydrophobic. And depending on this core structure, and this core structure heavily depends on the pH of the medium. Now, once we use different amount of hydroquinone, so that actually hydroquinone actually changes the pH of the solution. So as the pH of the solution changes, the core structure also changes. So once the core structure changes, we get actually different shape of nanoparticle. As you can see, when we use 50 microliter in the synthesis of hydroquinone, so this gives kind of like a spherical particle. But when we use 75 microliter of hydroquinone, it gives a nicely star-shaped nano. At the same time, like when we use much more amount of hydroquinone, like 150 microliter, so that time it gives like a overgrown star part. So by simply using different amount of hydroquinone, we can vary their pH, and this variation of pH actually change the shape of the core, and that shape of the core of the micelle actually governs the shape of the generating nanoparticle. Okay. Not only that, like I told, like the when we use a strong reducing agent like sodium borate, you can clearly see in the right hand side all the particles. Okay, it's a simple reduction like gold chloride solution as a metal precursor and trisodium citrate as the surfactant or the stabilizing agent, and you are using sodium borohydride as the reducing agent. You reduce it, and immediately it will form a nanoparticle. It's a red color nanoparticle. But the shapes are, you can see, all are spherical because sodium borohydride is a strong reducing agent. So it's reduced so fast, the system doesn't get enough time to crystallize in a direction wise. So they make a energetically the most stable the spherical part. But on the other hand, keeping the same composition everything, just change the reducing agent from sodium borohydride to ascorbic acid, which is a weak reducing agent. So that means you are slowing down the kinetics of the reaction, and you are giving the systems much larger time so that the different facets grow in different directions. So then you can see the left hand side, you can generate nicely anisotropic material. So you see, composition I'm keeping the same. Only thing I'm changing from a strong reducing agent to the weak reducing agent, and that itself actually gives the different shape of the nanoparticle. So those are the like a chemical things we can actually. So what are the chemical things we found? So we check that how it depends on the ligand, how it depends on their head group, how it depends on their pH, and how it depends on their temperature, how it depends on their reducing, on like whether it's a strong reducing agent or a weak reducing. Similarly, there are some physical parameters. Okay. I will describe the thing. Like the first physical parameters, which generally all the synthetic people we generally vary. So these are like temperature. Okay. The first parameter is temperature. You can see very clearly. Here also, we are keeping the composition of the material same, like gold chloride plus cetyl trimethyl ammonium bromide. So cetyl trimethyl ammonium bromide as the surfactant or the stabilizing agent, and gold chloride as the metal precursor. So this composition is constant. So now one I'm putting the gold seed and trying to grow this particle. So in both the cases, you see the reducing agent is ascorbic acid, which is a slow reducing agent. But keeping a slow reducing agent, if we increase the temperature of the reaction to at 60 degrees centigrade, you see the resulting nanoparticles all are mostly like spherical, which I have shown in the right hand. But keeping the conditions everything same, but if we perform the reaction at 28 degrees centigrade, that is at room temperature, then the same thing it generates a anisotropy. So that means the maybe remember like the few slides back, like when we are actually giving a harsher condition during the synthesis, it generates the spherical particle. But when we use a milder condition like the room temperature or below room temperature. So that times actually it generates the anisotropy. Similarly, you can see that recently we also got this. So like this simply that we can vary their shape by changing their viscosity of the solid. Okay, so by keeping same concentration, everything same, but only just varying the ligand concentration. So ligand concentration as it increases, the viscosity also increases. As the viscosity of the medium increases, so the diffusion of the metal atom or the reduced metal atom ions. Okay, so that speed actually reduces, or by that we actually we control the kinetic. So we move towards a slow kind. So that's why the atoms are arranged so nicely that they can actually generate the anisotropy. So you see, like when we actually vary the concentration of the CTAB between 5.5 into 10 to the minus 4 to 5.6 into 10 to the minus 2 molar. So that means we are increasing the concentration. You see how actually from spherical, near about spherical, at 5.5 into 10 to the minus 4. Then slowly it actually the tips are appearing and at highest concentration of CTAB, so we can see their shapes are now much more anisotropy. Similarly, like if the previous example also I showed, like the same here also one more the reaction I have shown, like the gold chloride, I took 1% trisodium citrate and then 10% sodium chloride. Sodium chloride here we use for to generate the blocking agent and use a 10 to the minus 2 molar silver nitrate. So silver nitrate reacts with sodium chloride, gives the silver chloride. The silver chloride which is sparingly soluble, so they block some acids. But this reaction, if we perform at 0 degree centigrade and 28 degree centigrade, so 0 degree centigrade is a milder condition. The kinetics is much more slower. So then it generates so nicely the flower shape nanowire. But the same reaction, same condition, only the temperature is at 28 degrees centigrade, which gives the spherical particle. Okay. And the below one, I showed like the when we use a heating method, it's just you take a 3 neck bottle and then add water, and then add gold chloride and trisodium citrate, and then heat it. So you could see like how actually the color changes and generate mostly the spherical particle. The other things like these colors in between, those are not stable. So finally, it turns out to red or different colors depending on the composition. But all of them are spherical. Okay. But when we vary the concentration of CTAB and increase their viscosity, you can see like the at different concentration with the increasing concentration of CTAB, the anisotropy at the beginning when the CTAB concentration is very low, it is spherically symmetric. Okay, it's kind of like a flower. It's a 3D ball with the spikes. Okay. But then it's become like hexapods, pentapods, okay, tripod, tetrapod, and then finally it's become a biplan. So you see the anisotropy is gradually increasing or it's giving a much more particle with a direction. So these were that reaction concern. Like if any one of you are interested, so then you can think about like how we can actually synthesize a large particle or small particle by using the same synthetic protocol. You see, like the idea is, you see, like when we use a fixed concentration of gold and vary the concentration of the ligand, so then we are basically keep on changing the ratio between metal and the ligand. Okay. So when we use large amount of TSC, so then per TSC number of gold atom available is much less, or we generally make a smaller particle. But when we use very small amount of ligand, so then per ligand molecule the amount of available gold is much less, much more. So we can actually generate a much bigger particle. So that's why when we use 3 ml trisodium citrate, so that means there are so many trisodium citrate molecules. Okay. So per trisodium citrate, the amount or the number of gold atom available is very few. We can generate a much smaller particle with a diameter of 15 nanometer. But when we use only 0.1 ml, which is 100 microliter in 100 ml, by keeping the concentration of the gold at 1.25 ml constant, so that time we can generate a particle with a diameter 95 nanometer. Okay, so that means just simply varying the composition or the ratio between metal precursor and the stabilizing or reducing agent. With here, the trisodium citrate acts both as the reducing agent and stabilizing agent. So that ratio actually allow us to vary their size, and we can generate very easily from 15 nanometer to 100 nanometer. Similarly, like the energetics also play a very big energetic mix, like generally in normal crystallization, so like there are three primary acids like 111, 110, and 10. So out of these, if you see the energy of the 111 acid is the minimum. Okay, so that means this acid is the most stable one. And then the next one energetically stable is the 100, and the most unstable facet is the 11. So that means out of these three, if anything is exposed to some impurity or something, so the 110 facet will try to block fast and will allow the other facets to grow. So that's what happens most of the time when we use the synthetic protocol where we generate a blocking agent like silver chloride. So the 110 facet always block, and the 111 and 100 facets are open to grow. So that's why we get a directional property of the nanotube. So this is how we can actually vary the size of the plasmid. So here I have described one of the synthetic protocol, so which is we call as the cumulative seeding. So that means we make each step a seed, and then we use the next step that as the seed to grow it bigger. Okay, and then again that bigger particle we use as the seed to grow a much bigger particle. So you can see, so this is a how actually the method. So here the metal precursor is my gold, and the trisodium citrate and ascorbic acid mixture as the ligand as well as the reducing agent. So by boiling this one, we can actually make a seed of size like 15 nanometer. Okay. So that 15 nanometer, then next step we use as a seed. So once we use the seed, we keep the other parameters like amount of gold we took 2 ml, 0.2% gold plus 0.5 ml 1% ascorbic acid plus 0.25 ml or 250 microliter 1% trisodium citrate. So this composition remains same, and then boil it for 30 minutes. So then by using that 50 nanometer seed, this particle will try to grow. So that will give me a 31 nanometer particle. Again, the 31 nanometer particle we use as the seed and keep the concentration of gold as per Wittgenstein and TSC constant. And then again boil it for 30 minutes, finally to give the 69 nanometer particle. Then by using 69 nanometer particle, we can grow a 121, and then from 121 we can move to 151, from 151 we can move to 290. So that's why, so first the here in the picture A is my C, and then from A I make the B, where B is again used as seed for the particle C, and then C is used for D, D is used for E, E is used for F. As the particle size increases, their plasmons also move. The smaller particle, the plasmon have the higher energy or the lower wavelength, so it gives a peak around 529. Okay, and as the size of the particle increases and moves towards 300 nanometer, so then the plasmon actually also moves towards 800. Not only that, the similar thing also we adopt actually for a nanowire synthesis. What are these nanowire synthesis? So here we use ethylene glycol, as I mentioned in my previous slide. The ethylene glycol, when we use as the surfactant or the stabilizing agent again, so that time we can get actually very thin nanowires. So here we took like 54 milliliter ethylene glycol and then heated it at 165 degrees centigrade. Why we heat it? Just to remove all the air which are trapped inside the ethylene glycol. So all the water as well as air we have removed, okay, before starting the reaction. And then removal of this dissolved oxygen, we add immediately 13.5 milliliter of 0.18 molar polyvinyl pyrrolidone. So this polyvinyl pyrrolidone, which actually we use as a safe-directing, okay, and then different amount of sodium chloride and also silver. The silver nitrate we kept a constant one like 4.5 ml of 0.28 molar silver nitrate. By using this one, if we heat it continuously for 25 minutes around 165 degrees centigrade, then we see in a stepwise. So initially it forms the seed. We can observe this color. Okay. So initially it forms the seed which gives the yellow color. So we know actually the seed color of silver is yellow. And the term also shows that they are all silver seeds. Okay. Now the next step, the step number 2, those seeds actually come close to each other. You can see how the seeds actually elongate by joining each other. Okay. And then third step, the seeds sometimes actually from the side also they come and then join. Okay, so they make a much bigger particle. Once they make a bigger particle, the other seeds are all being attracted towards the end, and that's the head of the rod actually starts increasing, and then finally we get a rod structure. So this I told like the how we can. So this method is a single step. Just one step, we mix everything and then put it and then heat it. So it gives a nicely grown nanowire. The another thing which actually stepwise we can actually synthesize. This is again a seedless synthesis. So without using any seed, just simply varying their condition. How we can actually synthesize different compounds. So here there are few chemicals like we use trisodium citrate, okay, and then we use gold chloride as the metal precursor, okay, and then we use silver nitrate as the impurity and ascorbic acid. Or we can add different amount of sodium chloride, okay, vary the sodium chloride concentration, or we can vary actually the pH. Okay. So first thing we did actually we vary the concentration of TSC. Okay. In variable concentration of TSC, so what we took actually 1.25 ml 10 to the minus 2 molar gold chloride we took. There I add 500 microliter sodium silver nitrate, and then at different concentration of TSC, if we add 250 microliter of ascorbic acid and then reduce it, it gives a shades of color solid. Similarly, once we keep the concentration of TSC constant, okay, but if we vary the concentration of silver nitrate, then the shade of color is different from the previous. Similarly, third one, we vary the pH by changing or adding different amount of HCl and sodium hydroxide, and then use the same method of reduction by ascorbic acid. We see a large range of change in the solution of the color. And more interesting, if we vary the sodium chloride concentration, then also we can actually vary the effectively their color, not only color, but also their plasma. So we can see, so like how we can generate it. Okay. So by using different amount of sodium chloride, so that means the last one, okay, the variable amount of 10% sodium chloride we do, and then we can find that we can generate different shape of these thorny nanoparticles. We call them as the edge of nano. And depending on the facet energy, as I explained, the highest facet energy is 110. So 110 facet will be blocked by silver chloride, and then the other facets like 111 and 110, they will try to grow and gives the sharp tip nano. That's the way actually we found different nanoparticles. Not only that, by varying the concentration of the A actually shows the variation of TSC. So once we vary the concentration of TSC, we could actually vary their plasmonic up to from 500 to 700. Similarly, if we vary the amount of silver nitrate, we could vary actually their plasmonics up to 8. Okay. Then if we vary the pH, we could vary the plasmonic from 500 to something like 1000 nm. But if we vary the sodium chloride concentration, then actually easily we can actually generate nanoparticle which has absorbance maximum up to variation from 500 nanometer to 1200. So that's why this is the most effective way we can generate different nanoparticles by simply varying the concentration of sodium. Now there are some other synthetic methods which are actually we are capable to generate the superland. So this is how simply we can do. We can just make a sodium borohydride based nanoparticle, which is a distribution of small particle, big particle, and other. So this badly prepared sodium borohydride based nanoparticle, we first try to thiol cap. So we just take a long chain thiol and then we adsorb on. So each of this badly synthesized nanoparticle will be covered by the thiol. And then if we add this synthesized nanoparticle with capped thiol into ethanol, so all these nanoparticles will be precipitated down. And the leftover top solution we can decant it off. And then this isolated nanoparticle, once we again add in a solvent, the non-polar solvent like toluene, and then put the same thiol ligand and reflux it, so then it actually generates a monodispersed nanoparticles, small particle. How it comes like? So this is we call as the ripening method. So that means the bigger particles, smaller particles. So the bigger particle lose their material to come down to the smaller particle, and the smaller particle actually will try to grab those things and comes to the equilibrium condition where the all the particles are of almost the same size and same shape. So this one experimentally we can even see nicely. So this is the first step where the sodium borohydride based nanoparticle, and this how actually it grows into like you see like the how they are so universally the identical nanoparticle, and once they are identical, so they will try to make crystals and make a super crystals of superland. So not only this, but also the nanoparticles, the defect of the nanoparticle is also a very much controlling factor, because the last lecture I told that as the defects increases, so their unsaturation increases, and that unsaturation gives their catalytic activity. So there are defects, several types of defects. One is the like a uh, zero dimensional, the point defects in a crystal lattice when both the is made by suppose like cation and anion like sodium chloride. When the 2 points are like the one sodium and one chlorine, they come out, so that they gives a vacuum. Okay. Or it could be like a one impurity atom jumps from somewhere and then sit on the interstitial position. Okay. So then this also can be a zero dimensional crystal, or even a nearby crystal lattice, one atom actually jumps and somehow incorporated inside the crystal. So that can also disturb the crystallization. So the first things like when they are, it could be a spot key defect or it could be a Frankel defect. Okay. The Frankel defects is usually like the when the one of the lattice point is substituted by a different types of atom. So those things actually by transmission electron microscope, by varying the angle of the dark field imaging, we can actually nicely we can find. So out beyond these zero dimensional defects, there are like one dimensional defects and also two dimensional defects are there. One dimensional defects, so you just remember there are like two different types of one dimensional defects. One is the line defect, and so these are the line defects. So line defects means like those could be like a edge defect. So you can see like the top A where one of the row of the crystal lattice points are missing. Okay, so this we call as the edge, and the screw defects when it's actually just rotate. Okay, so that actually screw dislocation. And the two dimensional, so there are like three different types. Like there are might be a twin bounded. The twin bounded, you see this dotted line. So this is a, if you consider this a mirror, then the both side atoms, so they are actually like a mirror image of each other. So these ones are like this yellow line you consider the mirror. So then you see they are actually mirror image to each other. This is twin boundary. Or it could be like a grain boundary. So like if a nanomaterials, if there are several nucleation zones and all are actually simultaneously growing and then finally connecting to each other, making a nanoparticle, it can give a grain boundary enriched defective nanomaterial. So you can see that this is one grain. So this pattern of the crystallization is different to the another grain. Okay. So these we call as the grain boundary defective nanometer. Or it could be a stacking fault. So stacking fault means like in a crystal, suppose the layerings are like this A, B, C, A, B, C, A, B, C. So this is a perfect crystal. Okay. So there is no defects or anything. Now, suddenly, if there is one particular lattice line is missing, okay, the one plane, like suppose this is A, B, C, and then you can see the left hand side, the extrinsic stacking fault, where the B layer is missing. So this we call as the extrinsic stacking. But when if there is an extra layer somewhere, it comes like A, B, C, then A one layer is missing. So you see the left hand side, the one extra layer comes, we call as the extrinsic stacking. And then when there is one layer is missing, like A, B, C, it's supposed to be next one also A, B, C. Instead of B layer is missing. So then we call it the intrinsic stacking. So these each faults or the each effective surface actually generates the unsaturation. And then by transmission electron microscope, you can easily see them how actually the stacking faults are there. So you can see here the one extra half plane is appearing or one extra half plane is missing. So this one actually the edge dislocation. Yes. So this is also how nicely we can see by the transmission. When this is a screw dislocation. Okay. And also like the by using our transmission electron microscope, we can easily see these structures. So like you can see the leftmost one, that is easily you can see like there are several grains. Okay. And here these black lines, so these are actually the twin boundary. And the stacking faults you can easily you can read out from here, like how the stacking faults are there. Not only this one dimensional, two dimensional, and zero dimensional, but there are some three dimensional volume defects also. So volume defects means either that is a crack or it could be a void. So suppose this is a nice crystallization A, B, C, A, B, C, A, B, C. And then suddenly there are a multiple atomic positions are missing. So then this makes a void. Okay. So in the nanomaterials also, when we generally do the galvanic replacement, then we can actually make a void. And these voids are these void in this. So you see, it's like the scientists, they can actually very easily they can make these different shaped nanoparticles. But the thing is, as the size is moving away from sphere, these particles, their stabilization also decreases. But if that is so, then we cannot actually make these highly energetic nanomaterials. But still, the scientists every day they can make this unstable nanomaterial. How can they make? With this unstability or instability of these nanomaterials, which are counter suppressed by the generation of more and more defective structures. So their crystal defects actually increases, which actually counterbalance their the destabilization. Okay. So till now, whatever we discussed, so we have now control on their structural and atomic manipulation. So now, does that control their special properties also? Yes, that is true. That they actually nicely control their properties also. So this is like that. This is the biggest applications of the nanomaterial which we in 19 in 2020s, like we can find. So they are mostly used in the biomedical. So the what are the biomedical applications? So any materials needs to have some special property which actually makes them applicable for biomedical. Those are like we should have a non-toxic material. Okay. And we whatever the reagents we use to synthesize them, there should be Benning stabilizing agents. So that means those actually cannot actually hamper the cell structures. Okay. And also it has to be, if you want to use them for the medicine purpose, so then they have, or intravenously if you want to inject them, then those things has to be stable against physiological saline concentration. Otherwise, once you push them, so in the blood immediately within few centimeters they will aggregate. Okay, so you cannot actually deliver them to the specific site where you want to deliver. And also, so they should be stable in the in the blood. So which is actually the stable, the blood pH is 7.35 to 7.45. So it's average like 7.4. So whatever the nanomaterials we are trying to synthesize, that has to be stable in this pH range. Okay. And also, most of the time, like when we irradiate the biological molecule, we see that the hemoglobins or the protein structures, either they actually absorb the light below 600 nanometers or above 1300 nanometers. So that means the biological window, which is actually most favorable for any photophysical therapy, which is around 600 nanometers to 1300 nanometers. Okay. So most of the nanometer we are trying actually synthesize. Okay. So those are stable in this optical medium. So that is like 600 to 1300. They should have active. Also, we have now ability actually to synthesize them anisotropically. Now, this due to this anisotropy, okay, we can actually excite them, and those tips structure or the edge structures, so those are highly Raman. So we can detect them also very nicely. And also like this, wants to deliver this nanoparticle inside the cell. So that means we should have a control on their size. Because if the nanomaterials is too big, we cannot actually deliver them inside the cell. So size variation ability is also very important. And lastly, like the we can actually we should use the nanomaterials not too much. So the dose has to be much low to both for cost effectiveness as well as to reduce the toxicity. So that seems the scattering property for the detection or their absorbance very high, and they are stable in the perfect physiological condition. So all those things favor. So we don't need really a huge amount of nanoparticle for any nanomedicine application. So which reduces both the toxicity as well as the cost. So I'll not describe very much like how exactly the mechanism works. Okay, but I'll show you some of the applications. Okay, so like this is I already showed like this type of nanoparticle which has a very sharp tip. Okay. So those sharp tip actually they focus the electromagnetic radiation. So that's the way the field actually enhanced a huge amount at the tip, and that field enhancement actually enhances the Raman scattering cross section. So that's why these particles are very good Raman actors. So they're very good Raman actors. So this is a rhodamin 6D spectra comes from these nanoparticles. So they really very high Raman cross section. Not only that, like this type of star shape of the popcorn shape particle. So what they do is like they absorb the visible light, and this visible light absorbs by simply the plasmonic excitation. So once they excite it, so those excitations they cannot come back as the emission because these nanoparticles doesn't have a radiative path. So how they will finally they will dissipate? So these actually what they use this excitation. So that initiates the electron phonon coupling means the electronic excitation coupled with the vibration of the crystal. Okay, so that's we call it the electron phonon coupling, which actually finally generates the phonon phonon coupling means the crystal lattice will start actually vibrating, and that generates actually the heat. So that or in a simpler way we can think about like the photonic energy is finally converted into the thermal energy. So that thermal energy conversion from photon energy it takes about the nanosecond. So once you see the whatever the excitation energy, it's completely dissipated through this one of the T. So if anything, any cell or any materials is absorbed onto these tips, so they will generate a huge temperature. It's something like 5,000 Kelvin. So nanoscopically, so that tip position they will try to destroy the cell. So by that way, actually, we can actually get the therapeutic activity. So this is shown by one of the examples. So where we took a star-shaped nanoparticle and then modify their surface by using different antibodies, okay, which allow them selectively absorb onto a cancer cell. And then once we irradiate with light, so they convert the photon energy to thermal energy and destroy the cancer cell. Okay, which actually we can simultaneously we can observe by recording the Raman scale. Okay, so initially the Raman will be very high, and as the time progresses, cells are destroying all the nanoparticles will come out from the surface. So the aggregation will reduce, and the Raman intensity also will fall. That's the way we can detect the therapeutic. So we can similarly like we can use different length of the nanowires, silver nanowires for the detection of mercury. So simply once the marker, so these are silver nanowires. Silver reacts with mercury and then gives a mercury as amalgam, and then that will actually reduce the length of the rod. As the length of the rod reduces, the Raman intensity falls down. Okay, and depending on the concentration of at very high concentration, the long length of the rod will reduce very much, and then Raman intensity will reduce a huge amount. But at lower concentration, the change of Raman intensity will not be that much. By that way, actually, we can actually detect mercury till 50 ppm, okay, simply by optical. So, which has a huge application in pollution control. Similarly, like this one I showed before, okay, like if we can synthesize different shape of nanomaterial inside a myself. And those materials which has flower shape can effectively use them for chemical conversion. Like here a specific example of 4-aminophenol to 4-nitrophenol. Okay, so 4-nitrophenol to 4-amino. So 4-nitrophenol, when we reduce by using this nanochemical, it converts to 4-amino, which by recording their absorbance, we can easily find. And then it shows that the flower shape or the nanomaterial which has a sharp tip, so those actually shows a very high catalytic. Not only that, these same flower shape nanoparticle also we can use for water splitting. This water splitting activity also we have shown here that this flower shaped nanoparticle which shows the maximum catalytic activity. Also, like at the beginning, I told like there are multi-layered nanoparticles. So that means the core is gold, then silver, then gold, and then again silver. The same way we can make also nanoparticle multi-layered nano, which actually shows the applications of fuel cell. Okay. One. So, these nanomaterials also shows the applications in the direct fuel cells. So like direct fuel cells means like we can make fuel cells from different alcohols like methanol, ethanol, ethylene glycol. So those things also we can use. Okay, so here are some examples. Like we make the nanoparticle which we call the nano alloy. Okay, if you see like the just simply one carbon like A, so you can see that the nano alloy which shows actually the electron density maximum. Okay. Similarly, the fuel cell applications you can see like in different like this is for the methanol, this is for ethanol, and this is for uh, another alcohol line. So you can see like the different activity it shows, and also like by increasing the concentration of methanol, ethanol, and ethylene glycol, we can see different fuel cell. So not only in the energy purpose, but also we can use different nanomaterials. So suppose this one we use like two different nanoparticles. One is the porous uh, silicon nanoparticle, and another is porous gold nanoparticle. We found that the restriction of aggregation. Okay, so this is the case of like Alzheimer's. Okay, disease. So Alzheimer's disease, like where the porous silicon nanoparticles, they actually prevent the aggregation. So they looks like this, and also this fibrillation kinetics, so this is the reduction of the aggregation. So that is actually the maximum for porous nano silicon, and then and the maximum for the without that. Not only that, we can also use the nanotechnology for detection of cancers, okay, through AFM techniques. Okay. So these are, as I told, but I'm not going to describe in details because those things we need to understand from the core of the project. Okay. Here also, like one of the good applications of the nanoparticle. So that like you can see the background, this is a kind of like a nano fibers. Okay. So we can make from the nanowires, we can couple them through higher techniques and then make a mesh. And on the top of the mesh, okay, so this if we coat a electrode material, okay, and then we modify the surface by a specific aptamers, then we can use this material for the specific detection of dengue serotype. Okay, so dengue has the four different serotypes like dengue, DNB 1, 2, 3, 4. Okay, so out of these, we can use a specific aptamer for a specific serotype, and then electrochemically we can detect it. So here you can see like we can detect them up to like 10 to the power minus 2 FFU per ml. So these are the few slides actually contributed from the lab students, and these are the new batch of students who have performed few of the experiments. So anyway, thank you. So if you have any questions, so you can ask me. So I'll be very happy to answer. Anurag,
Yes, sir. We are waiting for questions. Let's see.
yeah. So if there is any questions from this lectures, like you can ask them.
Yeah. No questions, sir.
Okay. Thank you then.
Yeah.
Okay.